Hello everyone, welcome to Calc 2. This is Megan Cheek, your instructor for the course, and each week I'll provide some videos for you outlining some basic terminology, definitions, formulas from the section, as well as some examples that would be helpful. So the very first section of our course is 6.1, which is titled Velocity and Net Change. So first off, I want to remind you that you should probably read the textbook before you watch my videos. When you put the two together, you're really going to have the best understanding of the material. So I do have some assumption here that you have read a little bit about section 6.1 from the textbook. So a couple of key things that were shown in this section. We have some notation that is a reminder from Calc 1 of position, velocity, and acceleration. And we also have the relationship between those three things. So if we take the derivative of the position function, we do get velocity. And if we take the derivative of velocity, we do get acceleration. However, in this section, we are actually going to be thinking using the reverse logic of integration. So if we integrate the velocity function, we end up with position. And if we integrate acceleration, that'll give us velocity. So something to remember when you integrate, if we have an indefinite integral, meaning no lower and upper bounds on our integration, then we do have to add a constant to the end. And so that is an important thing that we will need in this section. All right, another definition that might be familiar from Calc 1 is displacement. So displacement is something that's calculated over a time interval starting at time A and ending at time B. So displacement from A to B is defined as the integral, lower limit A, upper limit B, v of t dt. So it's the integral of the velocity function, which gives us the position function. But remember, when we evaluate definite integrals, we take the antiderivative and we evaluate it at b, and take the antiderivative evaluated at a, and subtract those two. So that was the fundamental theorem of calculus that helped us evaluate definite integrals. So that is the definition of displacement. Let's take a look at the definition of distance traveled. So here, what you're seeing is a very similar formula where we are integrating the velocity function over the time interval from A to B with respect to t. However, here you notice those absolute value symbols, where the absolute value of velocity is defined as the magnitude of the velocity or the speed. Okay, so if we take the antiderivative of the velocity in its absolute value form, we get the distance traveled as opposed to the displacement, which has nothing to do with the absolute value piece. So I'd like to show this in terms of a diagram. Okay, so when we integrate, we're finding an area. That's what we're finding. So when we're calculating displacement, and again, the displacement formula being the antiderivative of the velocity evaluated over the time interval from A to B. So displacement is going to be the net area found under this curve. So I just drew a random curve here over the time interval from A to B. And I filled in the area that is bounded by the curve and the x-axis along with the endpoints of A and B. So you'll see that the displacement of this function is the net area, or the area found by taking this region above the x-axis, which is positive, and then adding to it this region, which is below the x-axis, and that would be a negative region. And so when we add together that positive region and that negative region, combining those gives us the displacement. The distance traveled, on the other hand, if we wanted to calculate that, We're still finding area, but what we're doing is we're taking the absolute value. Now this section here doesn't need an absolute value because it already is positive. But this section down here, we need to take its absolute value to get its area and add the two together. So the important thing to note here is that this x-intercept plays a very large role in taking the interval from A to B and separating it into multiple intervals whenever you're calculating distance traveled. So I would have to integrate from A to, let's call this C, to get this area. And then I would have to integrate that same function from C to B and take its absolute value to get the absolute value of this area. And then I would add the two together to get my distance traveled. So one of the main goals of this section is that you understand the difference between displacement and distance traveled. So displacement is essentially what is the net distance that you are away from the point at which you started. So if you walk 3 steps forward and 2 steps back, your net distance from your starting point is 1 step. However, you actually traveled 5 steps altogether. So we've got a difference between these two definitions that involves taking the absolute value of anything that would be negative. All right, so from here, what I'd like to do is go through some examples. So my first example, sorry, my hand is in the way. I'll make sure to move it out of the way in time for you to be able to write. So the first example here, we're going to be given a velocity function, 6 minus 2t, and we're going to be given a time interval where t is between 0 and 6 seconds inclusive. We'll define that specifically as seconds. And the velocity specifically will be measured in meters per second. So what I would like to do is calculate the displacement and calculate the distance traveled. Okay. So how far are we after 6 seconds from where we started? And then what was the total number of units that we traveled, the total number of meters in this case that we traveled over this 6-second interval. So the first thing that we'll want to do is graph. So you do want to graph the function so that you can see if the entire function is above the x-axis or if you have pieces below the x-axis that you have to take into account. And it might actually be really beneficial in this course for you to get some graph paper where you're plotting things really precisely. It helps in terms of avoiding some of the algebra that you might have to do to get intercepts and intersection points and things like that. My paper obviously is not graph paper, but I'm going to try to graph it as neatly as I possibly can. So graphing this function 6 minus 2t, I might find its intercepts first. And so I know it has a y-intercept at 6, and it's got an x-intercept at 3, and it's got a negative slope. Okay. However, this doesn't exactly give me the graph I need because my time interval goes from 0 to 6 seconds. So that gives me the first 3 seconds. So let's see where I am when t equals 6 seconds. If I plug 6 into the function, I'll get negative 6. And now if I combine that, now I have a complete graph from 0 to 6 seconds. So what I want to do now is identify the region that we would get when this graph is combined with the x-axis and bounded by the interval from 0 to 6. So we would get this space right here, again bounded by the x-axis horizontally, bounded by this line, 6 minus 2t, and then bounded by t equals 0 seconds. Over on this side, if we bound by t equals 6 seconds vertically, and horizontally by the x-axis, and then the line, 6 minus 2t, we get these two regions. So, as far as using integration to calculate displacement, okay, so all we have to do here is integrate our velocity function, 6 minus 2t, with respect to t from 0 to 6 seconds. And that will automatically calculate for us the net area when we combine this positive region with this negative region. In the distance traveled piece, we do need to separate it into two intervals. So what I'll need is an interval from 0 to 3, and I will again integrate the velocity function with respect to t. And to that, I'm going to need to add the absolute value from 3 to 6, since that region is below the x-axis. So I'll get a negative region over here, a positive region over here, but I'll take the absolute value in order to combine the two. Alright, why don't we pause the video here for a second and have you work through the calculations on these. I don't want to show every tedious step of the calculations, but again, try to find the displacement for part A and the distance traveled for part B, and then you can unpause the video and go ahead and come back and check your answers. Welcome back. Hopefully you've worked through the calculations on part A and part B, and your answers are matching mine, 0 and 18. So we are actually exactly where we started because we went a certain number of units in the positive direction and in the negative direction. They turned out to cancel each other out. But when it comes to the distance that was traveled, we had 9 for the area above the x-axis and then negative 9 for the area below. And if we take the absolute value and add those together, we get 18. So just a quick reminder of integration here. When you integrate 6, you should get 6t. When you integrate 2t, you should get 2t squared divided by 2. And then the fundamental theorem of calculus has us evaluating that at 6 and 0 and then subtracting the results. So hopefully you remember your quick antiderivative rules. Alright, so that is it for example 1. Let's go ahead and move on to a second example, a second type of problem that we're going to look at in this section. So we also need to figure out how to start with a velocity function and use that in order to determine the specific position function. So let's say that we're given v of t equals the sine of t on the interval from 0 to 2 pi. And we're also given that the initial position, s of 0, equals 1. So what we want to do is determine the position function. Okay? So we want to find s of t specifically. So there are actually two methods that the book discusses in terms of finding this. And method 1 is basically something that you've already looked at in Calc 1. And so I'm going to show method 1 and I'll briefly discuss method 2. So with method 1, you want to remember that when you integrate the velocity function with respect to t, that you get the position function. But you get the position function with a constant added to it, and so our job right now is to figure out what that constant is.